Sorry about that. So the PLCs are typically the brains of any individual system. Sometimes you'll have multiple PLCs, like in manufacturing facilities or treatment plants for water, oil and gas. You could have many PLCs communicating with one another for all the different subsystems. The DCS systems are typically a little more robust, if not slower. They're meant for very large facilities, utility level, power generation, oil and gas stuff, facilities and pipelines. They typically have a bunch of extra safety features available to them. And SCADA systems are, depending on how deep you want to go down the rabbit hole of SCADA systems and what industry you're in, could encompass only the graphical interfaces that you guys would see on assembly lines, to the control interfaces and the control software in the main operator rooms for larger facilities, or for the water utility that I'm at, the SCADA system is all the way down to from the level transmitters all the way up to the data historians, the network equipment in between. So the controls, the SCADA systems, depending on where you're going to work, could be a very large system. So we're going to touch a lot of the basics. Sorry, I'm just going to, of each of these systems today. DCS is in a nutshell. They read inputs from field devices, send outputs to field devices. They'll execute logic. So that would be programs inside what to do with the information coming in and out of the field. And again, like I mentioned before, the DCSs typically handle tens of thousands of IO points. Imagine if you've seen any of those solar farms with 150 acres of panels, all of those get wired back to IO boards inside inverter houses. Those inverters will have hundreds and hundreds of data points monitoring all of the strings, all of the voltages, the amperages. All of that would get relayed up to a main controller, whether it's called a DCS or a PLC. Some companies, they'll call them RTACs, which I can't remember the name of that acronym at the moment. Real-time automation controllers. The DCSs typically will have some more redundancy features built into them, meaning instead of having some of them will have multiple IO cards where you'll wire back multiple inputs for the same device, and the cards will monitor that the wires are still connected. They'll even have multiple PLCs able to communicate back and forth and update and transmit the programs between each other in the event of a failure. And again, integrated safety controls, that's getting into safety as interlocking systems to shut down. To shut down in the event of failures, more than just light curtains. Does everybody know what I mean by light curtains? If I'm going too fast, it's, again, because I'm a little nervous. Slow me down, ask questions. PLCs, again, they can read inputs from the field. So whether that's for this example, such as a conveyor belt sending, I'm currently running pump sending a fault. Something is jammed. They'll send outputs telling the conveyor belt to start, telling the pump to reset, whether that's a VFD or whether that's an overload. So we do to try to get the system, whether that's inputs to a motor starter to run. They can execute logic. So the PLC programs contain logic to control field devices based on the current real-time information of the process system. PLCs can execute code very quickly. So this is the main difference between the DCS and the PLC. With response times below 1 second, typically in the 50 to 100 millisecond range. So for example, a PLC may receive a jammed signal from a pump. The process engineer responsible for designing this facility instructed the programmer that when the pump jams, turn on a second pump that is connected in parallel with the first one. So depending on the response times required, a PLC can do this very quickly. PLCs can typically handle a couple thousand IO points, given the limitations of particular platforms. If there's enough racks, PLC cards, even network access, PLC can handle thousands of IO points, which allows for some scalability. PLCs can also do some redundancies. This is going to be limited by the manufacturer and the kind of the level of processor that you buy. If you buy a cheaper entry level processor from Automation Direct, you're probably not going to get redundancy. But if you're buying some of the flagship models from Siemens, Allen Bradley, Schneider, they'll have some redundancy. And again, as I was mentioning before, these redundancies can be network links that will allow, if one of the processors has a fault, the other one to take over seamlessly. Processors can share IO racks. And some processors will have some safety control. Again, this is SIL safety stuff. Sorry. So, especially some of the industrial electricians, you've probably seen safety e-stops, some safety equipment. If it's an Allen Bradley equipment, it's typically in red and costs 5 to 10 times more than the normal relay for an e-stop. But if you're dealing with safety level, the integrity levels of the system, you can get some PLCs that will meet those. Some industries do require that. If you're doing a lot of work in oil and gas, especially for some transmission lines, there are some integrity check boxes that you need to meet before those systems can go online. I'll be honest, in 16 years, I've never used one in a manufacturing facility except for one saw, where if somebody opened any of the safety gates or broke any of the light curtains, the safety system would trip and break the saw. Not break, but actually apply a brake to slow the saw down so it didn't stop and they couldn't get jammed. So depending on your industry, you might see a lot of the safety stuff or you might not. There's a huge expense associated with that. Any questions? Perfect. Whoops. Oh, goodness. So again, the SCADA systems, supervisory control and data acquisition, is used to describe displaying real-time information about the process, such as graphical interface displays, controlling field equipment. This will be interacting with the system for setting set points, starting and stopping, acknowledging alarms, alarm logging, data logging, trending. This would be done through the SCADA system, logging information into databases. SQL databases are all over the place. So for logging alarms, events, live data, especially when you get into water, wastewater, you're going to be having to retain this information for the Ministry of Environment. One of you guys were saying you did some work in the food and beverage industry. A lot of your clean in place systems typically have to have regulated temperatures met for certain amounts of time. This information is going to be stored in a SCADA system somewhere. It's going to be put into a historian so that you can prove you've met your cleaning cycles for any sort of audit. Again, showing trending so operators can make informed decisions, and then sending and receiving different information. So sometimes you'll have, you could have a machine that would track its own data. One of you was mentioning that you did some work with the Toyopack PLCs. Those ones will typically actually have a processor and a touch screen, so like attached to it. They'll communicate with one another. You can actually load and view some pieces of software on the touch screen, but they'll also have their own kind of storage, which they could then push up to different servers. So the local machine only needs 10 pieces of information, but when you have 50 lines or 30 lines or a bunch of different facilities, all those pieces of information will get aggregated into a larger database. So typically the PLC can do process changes very quickly, but they don't do a lot of pushing of network data. That's not what they're really designed to do. So this is a photo here, which is Allen Bradley Control Logic's 5000 platform. So right now, this is their flagship, their top of the line processor. It has a whole bunch of features that some of the older stuff just didn't support. When you guys said you do a lot of work with the Allen Bradley Slick 500 platform, this is the upgraded version of that. If you've ever seen Compact Logics, this is, again, same programming software, but this one is a little more feature rich. So what we have here is a rack. So anytime you hear me or anyone use the word rack in association with PLCs, that's going to be this kind of box that the cards mount into. I think, yeah, so that is the PLC rack. That is similar for a lot of different platforms. So the GE Fanuc, Schneider has a rack. Not all of Allen Bradley's, but a lot of Allen Bradley's, they'll have a rack. Even some Siemens processors, they've got a rack that mounts the cards to it. In the back of the rack is what's called a back plane. So the back plane will transmit data from the cards to the processor. This here is the power supply. So let me load up a piece of drawing software for you guys. So see what I'm talking about. So this here is your power supply. So the electrician in the panel will wire 120, 24 volts to this unit. It'll power up the whole rack and it'll bring these cards online. In this particular rack, and this is possible, you actually have two processors. For Allen Bradley, you can identify them because they're the ones with this key on the front of them. Those processors for this family can be in any configuration in any one of the slots. So if you've done some work with some other processors and this looks funny, that's because for the Slick 500 and the Slick 5s and the Siemens and the Schneiders, all of them, the processor typically has to live only in the first slot. That's not the case for 5000. Your input modules, these are going to be your discrete or your digital input modules and your analog input modules. It's hard to tell what's what in this picture, so I'm going to move on to the next ones for identifying those. Your output modules will be your discrete output modules and your analog output modules. And then this one seems to have a couple of communication modules. This one looks like it's a control net card, which is a proprietary communications protocol for Allen Bradley. And these two look like they might be Ethernet. And I'm not sure what that is, just based on this picture. You're right, because I'm only sharing that window. Thank you, Harmeet. Let me. And then. If I do that, can you guys see that arrow now? Okay, yeah, sorry. So if I go back. So for this one, I had drawn here that these were your processors. You can identify that because of these keys. It's Allen Bradley. Some of them aren't doing keys anymore, but for the vast majority, you'll see this switch is to put the processor into different modes: run mode, program mode. We'll get into that later. This is just about being able to identify some of them. This portion of the rack. That's going to be your power supply. Whether it be 120, 24 volts. Again, depending on your industry, you could actually get 24 volt AC or 120 volt DC. How are you going to? Yes, this should be on the e-Conestoga, and if it's not, I will be putting it there. I think it's just, I will check and make sure that is available by the end of the day. Sorry, Saul asked if the presentation was going to be available online. Sorry. Oh, goodness. So in this example, we have, this will be a communications card. Oh, geez. So everything's skipping all over the place on my end. These are going to be your input and output cards. this just based on the color coding, that's going to be an analog input card. These are going to be digital output cards. That's an analog output card. Again, this is a communications card. Tatiana was talking about they develop their own controllers. So sometimes you'll have other devices that aren't Allen Bradley devices that need to pull data. And if you can't hardwire inputs and outputs to get that data between them, you can set up communications between your processors and those cards. I think that might be a little beyond this course, but I can absolutely point you guys in the right direction or get some examples. So I was touching on this earlier, but what is a rack? The rack is where the PLC cards are slotted into. The rack contains a backplane, which is much like the cardiovascular system of a person. The typical PLC backplane is passive and provides power to the cards and information pathways to the processor. So like I was saying earlier, the processors will get information from these different cards, whether it's the communications card, whether this is going out to a drive, this one's going out to additional racks, or you have IO coming into them. All that information is passed through the backplane to the processor. The processors can talk back and forth as well. A configuration like this, I'm assuming, is redundant in some way. That's the only time I've ever seen two processors in the same rack. What is a power supply? So the power supply supplies power for the PLC processor and all the cards in the rack. This is to turn the cards on, not necessarily for actually the IO portion of it. Power supplies can be redundant. Redundant meaning if one fails, the other one will take over. What is a processor? Processor is the brains of the PLC. This is what you are programming. So the cards are the cards, with the exception of possibly updating firmware for them. There's not much to do with them. All of the smarts are in the processors. You configure what cards are in what slots and what those inputs and outputs are going to be doing. The processors are responsible for scanning the routines, executing the logic, sending and receiving the data from the PLC cards, and many more things. Very, very process specific. What is a discrete input? Discrete is also can be used interchangeably with digital input. Input modules receive information from field devices. The field devices provide this information in the form of voltage, whether that's 24 volts. So imagine the PLC input card provides 24 volts DC. The PLC provides to the device through a common terminal. The device will be normally open. The device will send a 0 to the PLC in its normal state. It measures the voltage between the input and the ground on the case, and you will see 0. The device can be normally closed, and the device will send a 1 to the PLC in its normal state, meaning the voltage between the ground and the 24 volt. The ground in the case is 24 volts. So digital inputs are discrete. They are either on or off. So in this example here, would be a 24 volt input card. You can have 120 volt input cards as well, but you're essentially closing a circuit. So digital inputs are going to be monitoring if a pump is on, if a door is closed, if a switch is closed. Does that make sense? So here you've got example of wiring. You normally wouldn't wire wires like this, but okay, you do wire wires like this. I'm sorry, this is my first time, not my first time going through a lot of this stuff, but normally you'd wire that down to terminal blocks. I can show you some photos of some panels to get an idea of what you would actually see inside of a panel for those of you who haven't worked in them. Analog input modules. So input modules, again, they receive information from the field. So the typical configuration for analogs is 4 to 20 milliamps from the field device. This means that there's current flowing into the terminal, into one terminal of the field of the input card and out the second terminal. So it has to complete a circuit. 4 to 20 milliamps is used for analog devices. So this is going to be something that's not discrete. So if you have a pump that's on or off, but that pump can run at different speeds, your 4 to 20 milliamp signal is going to be what tells how fast that pump is running. So 4 milliamps would be set to 0%, and a 20 milliamps would be set to 100%. The processor will interpolate what the signal is. So at 12 milliamps, that would be 50%. 4 to 20 milliamps is by far the most common analog input, but there are other examples of them. For the ControlLogix platform, the card can be configured to accept different inputs. Other platforms, you would have to buy very specific cards for these other voltages. So here, for example, you can also read 0 to 10 volts from a field device. The methodology is the same. 0 volts would tell the PLC that the device is at 0%, and 10 volts would be at 100%. The problem with using a 0 to 10 volt signal is that if you were to lose one of your wires, it gets cut in a door, a terminal block shakes loose. 0 volts is a valid signal, so your PLC wouldn't necessarily fault check that. So seeing 0 volts would mean that the pump's is running at 0, where if you have a 4 to 20 milliamp and the loop opens or the wires disconnect and you start receiving 0 milliamps, then the PLC would be able to recognize that there's a fault condition there. And you can see this is showing that there's a loop going through like an amp meter. If I say an amp meter, I know the electricians know what I mean there, but does everybody else know what I mean by an amp meter? I'm seeing a lot of yes. Perfect. So the analog input is a good way to remember the inputs being you have some sort of variable device. So if there's something that's going to be changing, whether it's a level, whether it's a flow, whether it's a temperature, that's going to be an analog input. If you have something that either is or is not, it's in fault state, it's open, it's not open, is going to be digital. Output modules. These are very much the same. So if you have a digital output, if you turn the output on in the PLC, it's going to close a contact. Digital outputs are used to send signals to field devices. So if the PLC sends a 0, that means that the output is off. It means that the heater won't turn on in this example, in this slide. However, if in the PLC you send a 1 to that output is then on, then it will close that contact. If you imagine it like a relay, I say like a relay because some cars actually have relays inside of them and other ones do not. Some of them could be solid state. It will close that. It'll allow voltage to pass through it and then turn something on. So tell a pump to start, tell a light to turn on, tell a horn to sound, tell a valve to open. Turn on. Yep. And then, here's an example of wiring. So when the output turns on, the heater starts. Seems to skip over analog output modules, but an analog output module. Sorry, just making a note here. Analog output module is just for then telling a device that can modulate to do that. So if you've got a VFD, which is just a variable frequency drive, which is used to control a pump, you can tell the drive to run at different speeds. You would do that with an analog output card. If you have a valve that you need to have in a specific position, you could send 12 milliamps and have it move into that modulated position. So if you have something that's going to do something in a ranged response, you would use an analog output card. And again, these are typically 4 to 20 milliamps. You can do them in other voltages depending on what it is that you're controlling, but the vast majority are just 4 to 20 milliamps. Any questions on input and output modules? Oh, correct. So communication modules. So these are responsible for sending and receiving data over networks to field devices. So you can have any number of different types of devices. And 10 years ago, when somebody would talk about Ethernet module for PLCs, you almost exclusively were talking about how you communicated with the PLC. But now there's a lot of different devices out there which will talk on some of these control protocols. So for example, with Allen Bradley has ControlNet and DeviceNet. Those are proprietary kind of comm modules, like communication protocols that Allen Bradley has developed. The example here of Modbus TCP, that's a universal control protocol. These cards are designed to be able to send and receive information from different field devices. So sometimes these could be called field bus devices. If you're using, somebody had said Siemens, I believe Siemens has their own protocol called Profibus. These are just different versions of Ethernet or ControlNet. They're just sending data for the PLCs to be able to read instrumentation, or we could be doing PLC to PLC communications. Let's say you've got one PLC at one site that needs information from another PLC to know the level of a remote tank, and needs to know the flow at a remote site or a valve position at a remote site before it can open or close a valve. You would use these different field protocols. A lot of them are settling on an Ethernet based protocol just because it's widely available. But you will run into, especially with Allen Bradley, you will run into some of these proprietary control net and device net protocols, and Modbus is literally everywhere. It's an old protocol. I think we do get into some of that in the programming course, but that's just the basics of COM modules. Are there any questions? Perfect. So that is the end of this slideshow. Like I said, it was a very brief lecture on some of the basics and getting an idea of where you guys are with your experience with PLCs. Let's see here. I'm trying to get some photos up. Nothing to show here. What the heck? There we go. So this is an example of a PLC panel. I was trying to get permission from my previous boss. I've got a bunch of photos of some panels that I built, but I can't just show them without permission. So this is one of the ones that I did get permission to show you guys. So like I was saying, there's more than just a PLC in these panels. The electricians would know that, but the PLC isn't the only piece of automation equipment in any system. There's a lot of other components that comprise any automation setup. So you can see here, this is an old GE PLC, but it has a lot of the same parts as those photos from the slideshow. So this black pad here at the back, let's see if we've got better photos. This is going to be the back plane for this one. This is the processor. So this is the PLC, that's the brain of it. And then these are going to be your digital input cards, your digital output cards. The rack, it looks like there's a remote rack here. So there's a crossover cable, which would then expand that rack onto the second one. And these are your analog input and output cards. These cards are all wired. So this one is both, I believe. Oh, no, that's the processor right there. Yeah, these aren't, unfortunately, these aren't my photos. These are the only photos that my electrician sent me, and I didn't program this panel, and I haven't used the GE PLC in over 6 years myself. So you're right, that is a power supply because power is run into it, but I do believe that it also has an integrated controller based on that serial cable. All of your cards, sorry, that was I was answering Tatiana's question. All of these cards are wired down to terminal blocks. That is a big and very important component of any PLC panel. These terminal blocks, this is where your IO is then going to be wired up to your field devices. So you can see these wires, this is a good example of an old panel where these wires are labeled, and hopefully there are drawings that will tell everybody what these wires go to. These are going to be your analog inputs. So this is going to be your 4 to 20 milliamp wires with your shield. And we'll get into some of this stuff later. I just wanted to show some photos of things. It's a little better than just that slideshow. Inside the control panel, you're going to have some power distribution. So it says L2. So this looks like it's receiving power maybe from a lighting panel 2. Fuse blocks. These are going to distribute the power within the panel. And then the rest looks like it's all IO. These are your ground blocks. Without the drawings, I don't know exactly what the wires are. This just was a decent, clean photo that I had permission to show you guys. If you guys have panels that you work with and you have permission to send photos, I can share them with the class by all means. If you've got panels with stuff inside of it that you don't know what they are, I get a lot of electricians who will send me photos of a panel asking me if I've ever seen a device inside of it because they have no idea what they're looking at. By all means, share. I like seeing them. And sorry, I'm going to show some drawings here. So this is an example of a control panel that was installed a number of years ago, 10 years ago now, at the Hagersville water pollution control plant. This is one of the panels. I believe I helped design it years ago. This is just an example of a drawing set. If you're ever programming, one of the biggest skills, and we will get to this in a couple weeks. We've got some examples and some assignments about doing this. But the most common problem that you're going to run into is you're going to get a call, you're going to have a machine, you're going to have a process, and you're going to be told it doesn't work. That is the extent of the information you will be told. Because nobody knows. If you find drawings on site, sometimes you're lucky. These drawings, learning how to read the drawings, very important. Here you can see just a brief network configuration. Something like this will allow you to see, okay, we've got a Compact Logix PLC. We've got some blowers, so air blowers in the motor control panels, and then additional Ethernet switches. So if you found this, you would know quickly that VFDs were connected to the panel. Probably going to communicate with them. This is going to be the layout of that particular panel. So when you're looking at a drawing like this one's nice and labeled. There's a front view. It's going to be a big double door panel. Looks like it's got lifting lugs, probably mounted on a concrete pad inside of a building. The back plane. So when you have a panel like this, you can see that the outer shell here This is going to be a steel, gray steel, or a stainless steel box. And then you have a back plane for the panel. That is what all the components inside that panel are going to be mounted to. So if we go back to this guy, you can see here, this is the panel itself, the gray steel. This white is the back plane. So all these components are going to be attached to that back plane. So you can see here a nice labeling. So these numbers, these bubbles, they should be associated with a bill of materials somewhere in the drawing set, probably at the end, which are going to be labeling wire duct, terminal blocks, power supply. You've got your PLC here. They've done a nice job of labeling the actual cards. So that's a 1769 IQ16. That's an Allen Bradley Compact Logics product line. You can see they've got side panels as well. So not everything fit in the back plane, or potentially this client needed additional shielding. So they wanted to separate their analog inputs from the rest of the power. This is an example of a power distribution drawing. So again, we'll go over some of the things we're looking at, but understanding, has anybody ever seen these drawings like this before? Has anybody not? Okay. Perfect. So this type of power distribution drawing is fairly common. So the first thing is they're typically read top to bottom and then left to right. When you look here at the top, you'll see that this is 120 VAC. So that's volts AC from a lighting panel. A lighting panel is just going to be the source. So that's going to be like a breaker panel that you would have in your house typically. And then the lighting circuit for this one, the lighting panel is A12. The most important information to pull from that is that you have 120 volts coming into this panel, and this particular one looks like it has an L1 and an L2, which means that there are two line feeds coming in, two 120 volts coming in. Right here, I'm gonna turn on my drawing thing again, sorry. Right here, these are circuit breakers. Circuit breakers are protection equipment. When this breaker says 15 amps, that means that should more than 15 amps be drawn through the breaker, it will trip. It's similar to well, I'd say identical to what will happen in your house, although these typically aren't GFI, ground fault interrupted. Excuse me. You've got some more circuit breakers in here. So this L2 feed for this particular panel has 15 amp coming in. This whole line here then is the same electrical voltage and the same amperage. You can see it's all connected down. So all of this is line, and just like electricity needs a circuit, you can read straight across from the 15 amp through the 5 amp breaker into this receptacle. It's a low voltage receptacle. It looks like they're calling it a general purpose receptacle. This one I know is for a programming laptop. So this is going to be mounted somewhere where you can plug a laptop into. It's not going to be for a power drill or a heat gun for doing shrinking wire labels. This is for allowing an integrator or somebody in the panel to power up their laptop. Here you've got another circuit breaker, goes down to 2 amps. There's a door switch, and then there's a light. So this door switch is mounted in the panel in such a location that when the door is open, the light is going to be closed, or the light is going to be on rather. So if we go back, we can actually see if they drew it in. So LS5, this is possibly the door switch. We can look that up on the bill of materials. So further going through the drawings, the second circuit here, or L1 actually, so the first circuit comes down, goes right through. So this is a control relay. So everybody said they knew what a relay was, I believe. Does anybody not know what a relay is? Perfect. So obviously a 120 volt relay, it pulls in, and there's information here off to the side, what pins. So there's a normally open contact that's wired somewhere. So this is going to be a line reference. So these octagons, ooh, what happened to my pen size? There we go. Sorry about that. These are line references. So 501, at least for this panel manufacturer, this is not universal. So don't take this as gospel for every drawing set you see. But it looks like this manufacturer, 501, lines up with the names of the devices. So you've got circuit breaker 501, circuit breaker 502 that lines up with these lines. If I'm going too fast, don't worry, we're going to cover this again. This is just really important, and I think it needed to be covered beforehand, because even to just understand how to read these drawings will really help with reading ladder logic, which we're going to start touching sooner in the course than we'll get to the drawings, the drawing review section. So if I'm going too fast, do tell me to slow down, but we are going to cover this again. So this circuit break, this control relay is then turned on by 120. The power then comes down to this power filter. The power filter runs into, my goodness, a receptacle, and then this UPS. UPS stands for uninterruptible power supply, is then plugged into that receptacle. UPSs, the same as you would use at home. A lot of people will plug their TVs, computers into UPSs. If you have a power failure, it'll keep it powered on. This is the same idea. So very good practice for PLCs is to keep them on, even if power's off. Yes, for most facilities, if the power's off, you're not going to be able to run any pumps. You're not going to be able to open and close valves because there won't be power to those devices. But turning off and on PLCs, although they're normally fine, there's always a risk that they're not. So good electrical panel design is to include UPSs. So coming down, so now this line, you'll notice, is in line with L1, but it is not connected to it. That means it's being fed from the UPS, and these are not linked. So if you were to try to measure voltage from here to here, you might get a voltage from here to neutral, but I don't know. I don't know why I said that. Electrician, would you get a voltage from L1 to 508A? Because there would be a potential difference. Yeah, you will. But if you were to drop L1, by drop, I mean if you were to close or open this breaker, as long as the UPS were powered, charged, you would not lose 120 volts here. So it will stay on. It will keep. You can see down here we've got what do we have? We don't have a main breaker off of the UPS. Typically you would like to see a main breaker here. Ooh. So Scott just sent this and I clicked on it and it opened right into my screen share, which is dangerous, but a nice panel. So are there more than one photo in this, Scott? You know what? I can move this off to the side.
There's just one.
Yes.
I do have some other ones. I just gotta get them on my work computer, but the quality isn't great on that one.
Let's see. I only seem to see a single photo.
Might just be the one. So just the one
Yeah,
on there right now.
that's a high voltage. Are those soft starts?
No, those are just
Scott?
manual motor starters.
Scott, do you want to give us a tour of this panel?
Sure. Yeah. So the main breaker coming in is just an ABB breaker. I think that one was
direct messaged me. I think Scott
400 amps.
That's fine.
The top
again, so then the main components of panels. So this looks like it is mounted to an external frame. So probably part of a larger assembly. Looks like there's a blower system in back here. So this right here is going to be a main high voltage breaker. So what's coming in the top here, 600 volts maybe. So again, this is going to be a higher, more industrial application than strictly PLC. So that looks like a high voltage breaker.
Yeah. One is
And
for separate heat input.
I'm looking for a transformer.
The transformers down
here.
We've
got
right.
Compact Logic's PLC. All your IO. Everybody see where I'm pointing here? Your IO looks like it's gonna come in the bottom here. PLC panel or PLC Modbus card potentially. So for anyone who hasn't worked in many panels, this is a really clean panel and a good example of just some of the random stuff that you can see in different industries. This is the backside of a touch screen. I can't tell. It might be a GE make. General Electric. Buttons. That's a nice panel. Did you build that panel, Scott?
Yeah, we built this
Scott was talking. I did
couple
not
months
hear
ago.
him. Oh my goodness. My speaker turned off. I'm sorry, guys. Oh, sorry,
It's all
Scott.
right. Can you hear me now?
I can hear you now. I'm sorry.
That's all right. No, I was just saying that HMI is a Schneider HMI. It's a
Okay.
Megaless.
Magellas?
Megaless is the version it's called.
Okay.
The software is Visio.
Mm-hmm.
But we use that because it has a Windows 7 back on it, so we can do scripts and different data logging with
Oh,
Allen Bradley stuff. Makes it
so
pretty
they
easy.
finally they upgraded from the XPCE edition.
Yeah, and we've just started getting the Windows 10 version now. So we got another upgrade one, but those ones are a little bit hard to work with. But I'm just trying to get a few more pictures here, so just give me a second. I'll see if I can send a few more close-ups. Let's see. But essentially, this whole system's for oil processing. So you got your main breaker. The top is all heaters. So those are all fuses for heaters. I think they're 60 amp fuse holders. So we probably got 50 amp fuses in there. The reason that there are a contactor above and below is because the customer wanted a redundant contactor just for safety reasons. I think this one might have been doing kerosene, possibly, processing kerosene. So they want a little bit more safety with that. So there's that. And then the two lower fuses there are more heaters. All the manual motor starters, those gray ones are Siemens. So they're the breaker plus overload together.
Okay, so they're not soft starts.
No, not for these ones. They're just one molded case together with circuit breaker and overload. So those are there. We've got a couple relays at the top. All of our systems have a phase relay as well. So if they have 3-phase power come in and they have it backwards or they lose a phase, it will send a signal to the PLC that will stop the system, right? So if they blow a fuse or something, it kills the whole system so that they don't single phase a motor overrun a heater. All right. And then bottom was our control options there, which we don't do a ton. Mostly we do all the micro logics, like the 1400 is kind of what we stick with right now.
Yep.
But we do these every so often. So
Now that's it's all 24 volt IO. Is there built on IO in that one? It's like the L16 something, L23 ERMs or whatever. It doesn't
possibly on that one.
I'll nerd out with part numbers.
Yeah. That one, yeah, I'm not too sure. I think that one was just power supply, and then everything else you just adds the rack there. Let's see. It's kind of hard to see.
So this is a good example for everyone. So I had said earlier that typically most PLCs all have racks. So a rack is really convenient when you want to lay out and know exactly where your spares are. This Compact Logic's platform that they're using here is another Allen Bradley platform, but it's module based. So you can actually see here where so this, oh my goodness, this software, sorry. You can see here and here, the cards are actually separated. They slot together like Lego pieces. And then this is a bridge connector. So there's, so you know what? I'm not going to say for certain that is, but you can get these end caps. So this end cap would actually report back to the processor. It's the end of this particular module. And then here, you could actually skip over to another rack, and they will do some interconnection. That'll be a power supply to power these 3 cards, or this could be, it looks like it might be a remote IO. So even though I said earlier, most things have racks, there are platforms that do not. Sorry, Scott, did you have more?
Yeah, just give me 2 seconds here.
So
Let's see if I
there
can-
is some HMI work in the programming one, which is the 1351. Are you enrolled in that one as well?
Yeah, I should be enrolled in 3, the fundamentals, introduction, then advanced PLC.
Yeah, so I am doing 1341 and 1351. I don't know of the other one. I don't know who's doing that yet.
Gotcha.
I don't have a contract for it. It might be me, it might not. But there is some HMI work and there is some PLC work. Like I was saying, my colleague, you'll see at the bottom of the course outline, his name's Quentin. He kind of developed this program, but was unable to take the contract for it. And so he works for the college, but he also works for what used to be a competing engineering firm that I competed with when I was with an engineering firm, and we worked together on a number of projects. And with my, sorry, this is a long story that you guys don't necessarily need, but where I work now, I actually bring him in to do contractor work, and he asked if I would be interested in trying my hand at teaching. So that's how I ended up here. Not that any of you asked. All right, well, Scott looks for more photos. Let's go back to the drawing. Does anybody have any questions? I'm throwing a lot at you guys, and let me tell you what this week, what we really need to grasp, what we have to understand this week is a lot of the basics. What is the PLC, the different types of cards and what you can do with them, the difference between digital inputs and digital outputs, analog inputs, COM modules. Oh, there's another drawing.
Try that one. Hopefully that's got the full folder.
And I just can't stop just
Lost
clicking
the
on
screen. There we go. Yeah, so hopefully those have a few more close-ups.
the back side of the. Yeah, so you can see here your field IO, or I guess the stuff that's coming from your skids coming up through the bottom of the panel. This is going to be your terminal blocks to connect up to your IO, probably some signals up in here as well. Is this 600? 340?
I think this was 480.
480? Yeah. So yeah, this is just a main breaker. This is going to be old hat for the electricians, but this type of breaker will actually reach through. This is kind of a remote arm kit that will connect through to that hole. And if he has a photo of the front of the panel, there's actually going to be a rotary switch to turn on and off the main power feed to the panel. These up here, I think you can see my mouse. These are going to be your fuse blocks. And then these are conventional across the line starters. And now you were saying these are seriesed up for redundancy. So they both have to close for anything to go to make sure you want them. Are there 2 outputs for these?
Yes, that's correct. Yeah.
Yeah. Okay. So that type of, when I started talking about SIL, the safety integrity stuff, this is an example of an industry where you could use safety equipment and wire up 2 sets of IO to a safety rated starter and all of that. But this is typically what you'll run into is people will instead companies will instead buy 2 starters at $80 to $100 a piece and a PLC and wire up twice as much IO and still make out $5,000 less than what it would cost to do the same thing with safety equipment. Lots of added expense. And then the user's saying these starters have built-in circuit breakers,
Correct.
or are those just start so you can like across the line start it?
So that will trip. So if it's a short, that will trip like a circuit breaker. So it'll trip at 45. And then there's also another where that little blue button is on the top right there.
Reset
That's where the overload is. So that would be the overload trip.
Timers are just normal relays.
One's a timer and one's a relay.
Okay. Yeah. All right. So again, we're looking at here, compact logics. This is, I forget the product name. I think it's an L23 something or another. It's got a bunch of 24 volt onboard IO. So there's DC inputs and DC outputs. I know that because Allen Bradley color codes their stuff. So if you got blue input cards, DC inputs, DC inputs, DC outputs. This is, I can't tell if that's an analyst. That's an output card. I can't tell the color. This one looks brown. This
Yeah,
is
I think that one's output.
This is output because of the way these lights are arranged. So there's 16 points. It could be a relay output card if it's orange. This is brown. This is an analog input card. And this looks like it's an analog input and output card. So to save on IO, sometimes you can get combination cards that do both. These do not connect back and forth. So you can see here that these cards slot in the top. These little white tabs will actually positively slide over into the card to the left of them. And this chassis is complete. So if my memory serves me correct, there's a limitation with this family of processor where the power can only supply 4 cards to the right of it. After that, you have to end the chassis. And then this is an Ethernet IP extension module. So there's 2 Ethernet card ports here. So they're actually, you're likely reading this IO through the Ethernet switch up top. This will sit on the Ethernet network, and then you'll pull these 2 cards as well. And then this is another power supply. And then for the compact logics family, you've got this, which is a left end cap and a right end cap. So you actually have to delineate these. So instead of a rack, you can build a custom sized PLC for anything you want, as long as you've got enough room for it. But you're limited to, there's some design limitations for this family. Was that too much? Am I helping for you guys? Or how do we, for you guys that are new to PLC, how do we better get to catch up and learn better as the course advances? Oh, Ulu, I'm not 100% sure. I want everyone to get better. If you have questions, if I'm going too fast for you, please stop me. Like I said, I've been doing this for a long time and I can talk a mile a minute. And if you're not getting what I'm saying, please ask some questions and I'll try to rephrase it. I'll try to, I will do my best. So you don't feel like you need to catch up. Does that help answer? There are labs for the programming side of this. And there are some more assignments. There's a small quiz for this week. But if you feel like you're falling behind, please ask me as many questions. I know it sounds kind of cliche, but there are no stupid questions. Like, just don't leave questions unasked, because I can fly over something that I just assume everybody knows because I've known it for 16 years and I don't think about it anymore. And it's hard for me to sometimes put myself into the seat of somebody who's literally never seen any of this stuff. It's hard. Some of you guys were saying during your introductions, like you're trying to absorb and doing some of this stuff on the job. And I've been there. I've been thrown into a new, where do I get electrical schemes like these drawings. I think there's some material that's already preloaded in eConestoga. Again, I need to make, there's a setting in there where I can make things available to you or not. So this course was developed by Quentin. He was supposed to teach it. And then I'm not exactly sure. COVID waylaid a bunch of the programs, and I need to make sure it kind of all lines up. There's a bunch of dates. So I know there are classes to talk about this electrical stuff. And we're gonna practice going over some of these basics. Is there anything that I've skipped over that you want to ask right now?
Hey, Ryan.
Hey.
Just a quick question. One thing on the communication module side, it seems there are different protocols like control net and device net. I'm hearing in the industry sometimes they're talking about Ethernet IP. I'm just curious, what's unique about Ethernet IP and how is that different from like control net or device net or anything of that sort?
So Ethernet IP is a funny one because Alan Bradley kind of tried to coin Ethernet industrial protocol as their own, but it's actually kind of it's CIP, which I believe is just called like Common Interface Protocol. I'd have to look that up, but it's really just Ethernet. It's how the how do I explain that? If I can show you, well, I feel like if I start showing you my VMs, it might be too much, but maybe I'll do it anyway.
I mean, sometimes from my side, I look at some SMC products, and those products have some communication over control net, device net, and Ethernet IP. So sometimes it's a little bit confusing, which one is appropriate for the application, and don't like overdo things, but try and make sure that it's simple for the application, right?
So all three of those are kind of Alan Bradley, proprietary names. So if there's a device, let's say the device you're talking about is a drive or a flow meter that says Ethernet IP or control net capable. Likely what that means is that they've worked with Alan Bradley to develop some sort of like a link, like a an EDS file that would allow you to easily pull data and communicate with that. So that is something that I think we will get into in the programming one, the PLCs. This particular course is more about drawings, identifying the processor. We will get into the specifics of how the PLC works and the introduction of programming. We can talk about IP stuff later. And if you have specific questions about devices, I can try to answer them. But I think that's a little further than we want to go today. If that does that answer your question, or
Yeah.
at least,
Yep, that's fine. Yeah, we can look into it as we progress with the course. Yes.
yeah, at least dodge it for now.
Yep.
Okay, Tatiana. So, so maybe this is something that I should have started with. When in electrical theory, and maybe this is where Tatiana is asking a question, for 120 volt circuits, your power needs to move from your line through to your neutral. So it has to go from hot to neutral. So the very basics of what we're looking at here is CB501 powers your control panel power failure, your power filter, and will supply power to your UPS. CB502 allows power to pass into this receptacle. When you move down past your UPS, CB510 will power up this programming receptacle. So that's not a programming receptacle. It's just a very low rated normal receptacle. 5 amps is very low for a receptacle. Typically, you would see that at 15 or 20, depending on the type of receptacle. CB511 here is supplying power to the PLC power supply, and 512 is supplying power to the PLC power supply. We go back up here to the layout. You can see here we've got compact logics. We've got input cards. This is a power supply. This is that how I was talking about an interconnection cable. And that is another power supply. So if you were looking at these drawings and there was a problem that some of the cards weren't turned on, this is a drawing you would go to and go, okay, well, is CB512 tripped? You would use these for troubleshooting purposes. So when you look at these drawings, you would want to read from left to right, because if these circuit breakers are open, then this, I'm gonna do this in green. So power, in theory, will come down. If this circuit breaker is closed, we'll go through. This receptacle will have power, and now you'll have a load. So you could plug your laptop into this receptacle and you'll have power. If it comes down here and this receptacle is closed, that will complete the circuit. This power supply will turn on and your processor will turn on and your second power supply will turn on. And then this will go back up to neutral and this will complete that circuit. We've got a 24 volt power supply here. I have no idea why that changed size. Power will come in through here. Neutral back out to the UPS. And that, okay. I clearly don't know how to use this software. Yep. Perfect. Okay. The 24 volt section. I'm sorry, I have to delete these now. Does me tracing the wires out like that help, Tatiana? With the power supply, the 24-volt power supply, you can see here in this drawing, they don't have this means, I'm assuming this means that they don't have enough room to put all the details for that. So it says sheet 7. Yes, perfect. So here you'll see this again, it's this branch in here is separate from 120. This is 24 volts DC. So when you're looking at these, especially if you have a meter and you're troubleshooting a panel, it's good to follow that. And you know this is 24 volts. At the bottom, you can see 2601, and this says 2601. You can see that there and there. That's a line reference. So that means 601, based on what I'm seeing here, that means that this continues over on page 6. And this 2521, well, this is 5. So that means that the 24 volts continues up over here. Oh God. All over the place. 24 volts comes down. These are fuses. So a little different than circuit breakers. Fuses are circuit breakers that only go once. You can't clear a fuse unless you've got a bag of them. You can see here it's saying sheet 10. These are DI cards. So this is obviously the wiring to supply power for the inputs and output cards. Further down the 24 volts, we have an Ethernet switch, system OK lamps, analog loop power supply. So you can see that looks like the end of the 24 volts. Erase these lines and move on. The next drawing here, again, we're back to 120. It looks like it's all fusing now, no more circuit breakers. And this says plant effluent flow. So that's a flow meter. That's a flow meter. Aeration tank, DO. That stands for dissolved oxygen. This is, again, specific to wastewater. So these different devices are just being powered by 120 again. So power will come down through the fuse. If the fuse is not blown, out to plant effluent flow meter. If the fuse is not blown, these ones are spare. We've got a sludge flow meter. This tag here is going to be specific for a client. Not all drawings will have a tag like that. That is going to be referencing the device likely in the PLC. So HST obviously means something to this end client. I can tell you that that's actually Hagersville sewage treatment. STP is sludge transfer pump 3. FT1 is flow transmitter. And STAAI is, I believe, status analog input. That is just an example. There is no universal standard for tagging. Just sometimes you will have very nice drawings that will have that. This for Logix 5000 will show up in the processor. Skimming down again, the rest of these are 120 volt devices. They just have power or they don't. Based on the fuse. This is where we get into IO. So this drawing here shows we've got a 1769 L35E. That's an Allen Bradley Compact Logix processor. This is a Compact Logix processor input module. And Each input module has 16 individual inputs, and this drawing will show this terminal block 516. It's commented up, and then I100 is the aeration tank 1, gate 1 in auto. Input 1 is aeration tank gate 1 fully open. I'm not going to go through every one of these, but they have the tag for that input, and you can see that this has been grouped: tank 1, tank 2, another input card. This one's marked future. We've got genset faults, on and on. They're showing symbols here. This, if you're familiar with drawings, electrical drawings, you'll see here. Oh my goodness. Yeah, that seems to be what's happening, Vincent. And I'm trying to remember to not scroll. Yeah, that's definitely what's happening. Yeah, it's big. Thank you. This indicator is a generic contact, and it will show up in ladder logic. So that is what you would see for a normally open contact of anything, whether it's a relay, whether it's a switch. It's a generic normally open, and when we get into the programming, we'll see that as a normally open or examine if open. Here, this is a switch. That's your handoff auto switch over here. The next drawing, power supply. They've obviously laid this IO out based on the order it's come in. More digital inputs. This one indicates that there's something going on inside that screening system. I would then try to go and reference that drawing if they have the drawing for that vendor package. This is this right here. So your CR504, that's the control panel power fail relay. And then these are your outputs. So you'll see here, it's showing, oh, I guess I didn't even touch this earlier. So at the top of the IO cards here, it's showing 24 volts coming down to one terminal block, and it's being jumped all the way down. So all of these terminal blocks in the panel will be commented up, and then individually each input has their own terminal block on the other side. TB5, this will line up with a certain section of the panel. 24 volts passes through this device in the field. When 24 volts comes to this input, that input will turn on. In the program, you'll see on that input, it'll go from 0 to 1. There'll be a light on the front of the panel. It will turn on, and then the common runs up through the card and out. So you're just completing that 24 volt circuit. That's how the PLC knows it's turned on. This is ostensibly the same for 120 volts, just a different voltage. Different cards may have slightly different wiring configurations. That is something we can cover later, and it's available in every one of the manufacturing. Like every one of the cards has their own wiring diagram. For your digital outputs, this particular one is showing it's controlling a relay. So especially for 24 volt relays, there's a lot of field devices that are not 24 volts, they're 120. So you'll have 24 volts comes here, it runs into the card, it'll run through the circuitry inside the card. When the card is told to turn on, in this case, the gate open command, it will then pass power through this relay. A1 and A2 are wired up. So you have your 24 volts into A1, A2, that's your coil in the relay, comes out, goes back up 0 VDC. Your 0 VDC will be run common down these relays. So when the relay coil pulls in, it closes your contacts and this gate valve will start to open. Likely these are called interposing relays. They're used when you need to switch voltages. So this is probably 120 volts, even though it's not listed here. 24 volt relays with 120 volt contacts. Questions? All right. More outputs. Analog inputs. So these are a little more complicated, and I'm not sure how in depth some of the other classes lessons are going to go for wiring analog inputs. Really, it's especially for today, just the basics of what an analog input is. So this is showing a lot of information. This is an example of a really good drawing, in my opinion. This flow meter has 120 volts coming into it. There's wire labels for that, and it's grounded out on this side. So it has its own power. It is not being powered from the PLC. It has signal wires coming out of it that get wired into input 10-0. And that's all the information we get here. We do have a tag for what that device would be inside the PLC, but we do not know the range of that. So we know that there's a flow meter. Sorry, my speaker is turning off. So if people are talking, I'm gonna have to figure out why that keeps turning off. We would then have to look for some sort of calibration report, some sort of documentation that says what 4 milliamps and 20 milliamps means on this flow meter, because there are flow meters on 1-inch lines, and then there are open channel flow meters where it could be 5 liters per second is 20 milliamps on one, and 20 milliamps on the other could be, I don't know, 1 million gallons a day. And yes, sometimes I do run into gallons, millions of gallons per day, even though we're in Canada. There's a couple of different ways to wire 4 to 20 milliamp inputs. You don't really need to know that. Just you can be aware of it for your future selves. You'll see here, this device, because it receives its own external power, has enough power to power its own loop. So it does not need power from the panel. Where you see this, it looks like a valve positioner. Valve position feedback actually receives 24 volts from the panel. It goes out to the device and then loops back in, and there's a jumper to return that to 0 VDC. That's called a loop power device. If that shows up anywhere on a quiz, it'll be bonus marks, because that's just something that'll burn you in the future. Just wait for it. Analog inputs, analog outputs are the same as the inputs. They're actually typically a lot easier because you know what the range is going to be. Most of the stuff that I've ever sent a signal to is 0 to 100% or whatever. It could be a specific type of pump that runs 0 to 20 liters per minute, and 20 milliamps is 20 liters per minute. Pretty straightforward, but the configuration is different for every device. This drawing right here is called a Lamacoid schedule. You won't find that everywhere, but it really just lists, this is for the manufacturer. It lists all of the little tags that will show up on the panel. So This is the front of the panel. This one's going to give you your rating for it. This is probably the only, this one and the power one, multiple sources of power, hopefully are on every panel that you guys go into. The electricians probably know that that's not true for every panel. These other ones are labeling the different devices inside the panel. And then this is your bill of materials. So a good drawing set will list all of the different devices inside the panel, the part numbers. So manufacturer, you got your enclosure, your depth plate, that's going to be the side plate we were talking about, your back plane, door switch, shelves, ground bars. I don't think I need to go through every one of these, but a bill of material is a very important thing to have, especially as programmers. If you end up in a panel and something's broken, you probably need to try to find a replacement for it. And if you don't know what they originally had, or if it got burnt out, anyways, I'm rambling. Are there any questions? Oh, terminal block layout. This is just labeling all the terminal blocks and the wires that come in and out of them. Any questions? I know I threw a lot at you.
Hey, Ryan.
Hey.
Hey, I know just earlier, not about exactly what you're talking about now, but earlier you're talking about redundancy, and I'm not sure what that is or how it's beneficial. You were talking like it's built into panels as per like customer requests kind of thing. Just what is redundancy?
All right. So redundancy for automation systems is kind of system integrity. So if you have, let's say you have a 24-volt power supply, and if that power supply fails, you don't have any more 24-volt in your panel. If you have a redundant power supply, you would then have two power supplies in your panel, and you would have a third device that would then switch between them. So that if power supply 1 failed, power supply 2 would keep powering your 24-volt circuit.
Okay, so it's just kind of available just in case.
Yeah, duplicate. So that's
Okay.
when you get to PLCs, there are some PLCs that will actually allow you to have redundant PLCs in the configuration. So you can have processor 1 and processor 2 all monitoring remote IO. And if they would have a redundancy unit between them, and should one of the processors fault or lose power or something, the other one would immediately take over. So
Okay.
it's limiting your points of failure. So you can get crazy, where I've seen for one manufacturing plant, they had 2 identical IO panels and 2 processors. So they had 3 panels for their system. So if there was a fault in one of the panels, everything was wired into both so they could keep running. They would fault. They had a 5-minute changeover for moving one wiring harness over to their separate IO.
Right. But then your downtime's only 5 minutes.
Their
and you're
downtime was
fine.
and their processor never faulted.
Gotcha. Okay, cool.
Yeah.
Thank you.
No problem. All right. So, okay. Gotta close that. Oh. Okay. So to summarize, all the importance, like today was basics. I know I threw a lot at you guys. I'm going to post some reading material. I'm going to make sure that this PowerPoint presentation is available to you on eConestoga. I think it's just a matter of me clicking make available. I'm also going to post the video of this lecture, and I think I'm going to have to re-record me going over the course outline, but I'm going to make that available to you guys as well. So you get to listen to me go on about this stuff for 2 hours again, if you wish. Yeah, if you guys have any questions, I got that's all I really got for you guys today. I know we're 45 minutes early. Typically, some of the other classes have some assignments to work on, and I just don't have much of that for you guys today. So I'm just gonna looking at this course material here while I'm going through this.
So I have a question. Are we talking about just non-safe PLCs, right? Are you going to cover topics about safe PLCs?
I believe there's some information about safe PLCs in one of the next lectures, but I don't know if we have any to actually work with. Is there something specific you wanted to know about safety PLCs?
Just general information at the beginning.
Yeah. The safety PLCs, safety PLCs, they look a lot like normal PLCs, but they have additional features inside of them. So they will do things like fault check wires. So like I was mentioning before, when I believe was Scott who, yeah, Scott sent me some photos where they had 2 motor starters. They'll actually they'll have safety devices in the field where they'll wire multiple inputs and multiple outputs to those devices. The safety PLCs will have monitoring for those specifically to know that, to make sure that a door is closed and there's 2 inputs for that, and the safety PLC automatically checks and automatically monitors both of the inputs to make sure that they line up. Inside the processor itself, there's actually additional routines that run to check and make sure that the program is the same. So when you have the safety section of a PLC, that is specifically for the safe shutdown of a manufacturing system, of a gas turbine system, that needs to happen in a specific way and very fast, and needs to meet specific safety integrity, system integrity levels. SIL3 is the acronym. And if you need to meet those requirements, you need to buy the special equipment. So it will actually monitor the program that's for shutting down, and then make sure that nobody can edit that program without special keys. There's a lot to them, and I think there might be some more in a lecture. You don't need to know too much about them today, just kind of that they exist.
Okay, thank you.
Did that help?
Yeah, thanks.
All right, so you guys should see a quiz available for today. Very short. It's due Sunday. Can somebody confirm you can see that?
I have a question about quizzes. So how does it work? What is covered in quizzes? How much time do we have to finish it? And so on, because I've never took such courses before, so it would be nice to have some general information.
Yeah, so I've not taught this course before, but I was looking through it, and the way it was described to me and the way I'm planning on running this course is that anything Any quiz, the quiz from today, you have until Sunday at midnight to complete it. It's not going to take you very long. It's open book. Use any of the material, look stuff up if you want. Submit it whenever you want. Does that help? And then you'll be able to, through Econostoga, you should be able to see it right now. So by pull
So
this up.
basically I can click to start the quiz and start working on the questions, look at the question, find the answer, then start next question. So it doesn't matter how much time will I spend
That's
on
right.
every question.
I've not limited it in time at all. So
Okay.
you have as long as you want. I haven't done a quiz. I was gonna practice with this one myself. To see if you can do one question and then move on to some and then close the window and come back and see if it saves your progress. I don't know off the top of my head. I just haven't had time to play with it. I didn't get access to this course material until this morning. So I've been.
So you don't know if you can switch questions and to work first, for example, on question number 5 and then return to question number 2.
Let's see. You can work on, so when I open this one up, all of the questions show up on one page. I can scroll up and down. I can see them all at the same time. It doesn't really matter. Yeah, you can work on any of them in whatever order you want. Just don't submit until you're done. And if I close out, I can come back in and say click continue. So it looks like you can leave and come back.
Okay, sounds good. Yeah.
Yeah, no, it looks. Okay. Any other questions? If you have any, I'm gonna take a break, use the washroom. I'm gonna come back and try to figure out the attendance piece. If you have questions, by all means, I'll be here for a bit. Where will you be? I'm gonna be posting the reading material inside the whatchamacallit, this course content. So every week you're going to have here as a student week, where'd it go? So under evaluations, you'll see quizzes. So there's the quiz for week 1. It opened up at 1 o'clock or 6 o'clock. And yeah, it looks like I have, bear with me. So there will be, yeah. So there's a week 1 intro to PLCs. It's just, I want to make sure all of the information in here is good. I'm going to add the video to this. You can't see this just yet because it's only available in the teacher view, but it will be there. And I'm going to do that today. And the reading material. And there's no specific books for this course. All safety PLCs have dual channel inputs. Not all safety PLCs have dual channel inputs. It is one of the most used features that I've seen. Again, in the 16 years that I've done PLC programming, I've only seen one safety PLC. So I'm not an expert, and I will look up more stuff if you have specific questions, especially in any of the coming labs. There we But yeah, if you guys want to take off or ask me questions, I'm gonna sit here for the next half hour trying to figure out the attendance. Send me an email if you have any questions, and next week hopefully I've got a better grasp of this technology. Yeah. Thank you.
Thank you, Ryan.
Okay. Have a good night. And again, if I'm going too fast, let me know next week.